1.1, all about functions. Let's do a kind of intro to functions. So this is going to be a very layered chapter about, well, functions and their graphs. So first we want to talk about how can they be represented. They can be represented in 4 ways. Verbally, I can tell you a sentence about a function. Numerically, I can make a table, an XY chart. Usually use what you've probably been used to. 1, 2, 3, 4, 5, 6. Graphically, you can make a graph and connect your values or just plot points. Analytically, equation with 2 variables, y equals x plus 1. That's analytically, right? 2 variables represented in this equation. So I have 4 different examples here to determine whether a relation is in fact a function. One thing we need to look for is there any input value that has multiple y values or multiple output values? When we look at the tables, they're kind of easy to look at, right? So we have right here, we have 1 input value with 2 different output values, so this is clearly not a function. And this one over here, this is a function because we have different x values with their own individual y values. So yes, it is a function. Y equals x squared. Now, if I were to graph y equals x squared, it'd look like that, right? Another way we can tell if a relation is a function is something called the vertical line test. If I bring in a vertical line all the way through, does it touch twice? It does not in this case. So yes, we got a function. And over here we have y squared equals x. What type of function does that look like? It's going to look something like this, right? Oops, I drew that wrong. So it'll be more like this. Does it pass the vertical line test? Absolutely not. So no, it is not a function. Not a function. If we're testing for functions analytically, what we need to do is isolate y. So when we isolate y here, we square root both sides. Get y is equal to plus or minus x. Anytime we square root an equation, you must include a plus or minus. Now with this case here, you have 2 different solutions due to the plus or minus. So we know analytically this is not a function based off of that fact. This below is what's called function notation. When we use f of x, g of x, anything along those lines, that's function notation. Because the x represents our input, and then f of x is considered our output. Okay? So when we are evaluating a function, like we are in this one right here, let's let g of x equal negative x squared minus 3x plus 5. And we're going to solve g of 1, g of negative 2, and g of x plus 1. So we're putting in 1 everywhere we see an x. So it's going to be 1 in here. Put a 1 in for x plus 5. Keep in mind, a negative outside of the x squared, order of operations, exponents first. So it'll be 1 squared times negative, so it'll be negative 1. Minus 3 plus 5. Add them up, you're going to get 1. Over here, negative 2n. Negative outside, squared, minus 3 times negative 2 plus 5. So it's going to get us negative 4 plus 6 plus 5. Add them up, you're going to get 7. Finally, this is one of the probably more difficult ones, and we're going to put in x plus 1 in. We got to FOIL the x plus 1. Okay, please do not just distribute the squared. I see that all the time. Please don't do that. So, and I'm distributing that negative 3, which I did not do to the second one here. This should be negative 3 plus 5. We FOIL it, it's going to be x squared plus 2x plus 1. So you're negative, you get negative x squared minus 2x minus 1 minus 3x minus 3 plus 5. Like terms, we're going to get negative x squared minus 5x. Negative 1 minus 3 plus 5 is 1. And there is our solution. So this is what's called a piecewise function. Okay, we have for different intervals on our inputs, our inputs are right here, over here. Okay, those are your inputs, and what we're going to do is by, like up here, we have x is less than or equal to negative 2 right here. That means for all x values we're inputting that's less than or equal to negative 2, we're going to use this function. Between negative 2 and 2, use this function. Anything 2 and bigger, we'll use this function. So right here we have f of negative 3. We want to find that. So where does negative 3 fall on our piecewise function? Right here. So therefore we're going to plug in negative 3 there. 4 minus 5 times negative 3, and it's going to get us 19. And then we put 4 in. 4 is where? 4 is down here. 4 is greater than 2. So therefore, it's going to be the x squared plus 1 part of the function, which is going to get us 16 plus 1, which is 17. Negative 1 squared. Negative 1 falls where? We're not squaring it because we're using this one right here. We're between negative 2 and 2. So your output's just going to be 0. Straight up 0. So let's find the values for which f of x is equal to 0. So all we do for these is just set 0 equal to the function and then factor. After we do that, set your factor is equal to 0, as you have all done before, and solve. You're going to get x is equal to negative 3 and x is equal to 3. So here we're going to find values that f of x is equal to g of x. So let's set them equal to each other. That's all we got to do. We know what f of x is equal to, we know what g of x is equal to. And then set it equal to 0. So we're going to move this over. That's probably the easiest, move these two over. And then we get x squared plus minus 5x plus 6 equals 0. And factor it. X minus 2, x minus 3 are going to be the values we use, which is going to get us x equal to 2 and 3 when we set them equal to 0. So, find a domain of functions and using function notation. Now, a little trick that we need to look at, and that's, well, of course, let's do the simple thing first, and that's if you're just given pairs, ordered pairs, like let's say the function consists of 0, 1, 1, 2, and 2, 3, your domain is going to be 0, 1, and 2. So in case you see that, that's how you would find that domain. But for all the others, when it's in function notation, you need to look for two things. One, when is the denominator equal to 0? So values that make the denominator equal to 0 are not part of your domain. Okay? You're not going to include them. 2, values that make even roots negative. Because you can't find a square root of a negative number. You can't. Okay? So these two things will make your domain not our real numbers, and these values you will not include in your domain. All right, some examples. So we have g of y is equal to square root of y minus 10. So clearly values like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 will make that square root negative, and we can't have that. So what values make this 0 and bigger? The values make that 0 and bigger are going to be 10 and bigger, right? So your domain is going to be bracket 10 comma infinity, close parenthesis. With our infinity symbols, we always get parentheses when we're in function notation, like this. And when the value is included in our domain, we're going to have a bracket like that. Now for this other one, we got square root of s minus 1 divided by s minus 4. Two things going on, right? 4 makes the denominator 0, so we can't include 4. S cannot equal 4, and also s must be greater than or equal to 1. So we need to write our interval notation with this in mind. So we're going to have bracket 1, because that's our starting point, because everything bigger than that, bracket 1, comma, but it can't be 4, so I can't go to infinity yet. So I'm going to make that 4, parenthesis, union, 4, comma, infinity. Because this reads it as everything bigger than 1, and including 1, except for 4. Okay. I hope this helps, and we'll see you in class. Bye-bye.